Hi, my name is Lydia Sohn. I'm a professor in the Mechanical Engineering Department at UC Berkeley. I'd like to thank the organizers for inviting me to give a talk about encoding with microfluidics and applications. So this story that I will tell you and about this project, it's a really based on a very productive and fruitful and great collaboration that happened by accident. And I like to tell people it can only happen at Berkeley. This work was done in collaboration with Mickey Lustig in the Electrical Engineering Computer Science department here at Berkeley. And I'll explain like how this actually happened by accident. It's a great story. So, my lab has really built its reputation on developing essentially a culture counter on chip using microfluidics. We like to say that we're doing resistive pulse sensing for screening cells, but this is really just the culture counter principle. And what you see on the slide is really an image of actual photographic image of a microfluidic channel that we've made, filled it up with red dye so that you could see it. It has filters, it has reservoirs, and it has electrodes that connect that will measure the current across that small channel that you see there. And you can see the dimensions of that channel. And the way we do these measurements really is we use those electrodes and do a four-terminal measurement of the current. You can see that schematic below, where essentially we're measuring a constant current when fluid is just filled the channel, and it's also referred to as pore. It's interchangeable. It's a historic reason for in my lab. And then when a cell passes through, a cell is is an insulator. So as it passes through, you see a drop off in current. And then once the cell all the way flows through, the channel once again fills up with fluid, and you see a rise in current. And again, this is just a culture counter principle of measuring or counting cells. Why does it really work? Well, essentially, this microfluidic channel is filled with fluid. We're voltage biasing it, so there are current streamlines or electric field lines passing through that microfluidic channel. And it was really Greg and Stidley who really showed us who used Maxwell's equations to actually determine what the resistance was if you were to measure a non-conducting particle or insulating particle that's flowing through this fluidic channel. And you can see here the two limits, whether or not the size of the particle, little d, is approximately the same size as big D, the diameter of the channel, or if it's much smaller. And you can see it's a nonlinear relationship with respect to the length of the channel, the diameter of the channel, and so forth. So going back to this picture that I have of our device and how it operates, despite all those complex equations, you can really just get a sense of really what you expect to see, that the pulse magnitude or the resistance would really be volume to volume ratio of the volume of the cell with respect to the volume of the pore or that channel. Now, we realized quite a while back that, we're measuring current across this channel, and the channel is filled up with fluid. And it's really like, as a parallel, it's really like a conducting wire. And we know from our basic physics 101 classes that the resistance of a wire will change per the wire's cross-sectional area. And so given that, we really came up with something that we like to call Node-Pore Sensing. And so here's a microfluidic channel filled up with fluorescein dye. And then what we had was a cell pass through it, an MCF7 cell. And you can see that we get this classic culture counter square pulse. But then when you change the dimensions of that channel, so we include a node, that's just this wider area, equivalent to increasing the cross-sectional area of a conducting wire, what you see is that that square pulse now gets divided into two smaller pulses. And why does that happen? Well, again, what you have is you have this cell, and remember what I just said in the previous slide, that really the change in current or the change in resistance that you measure is proportional to the volume of the cell with respect to the volume of the channel. So when the cell is in that narrow portion of the microfluidic channel, you see a huge drop off in current. You see a big change in resistance. And then when the cell enters into that larger area, the node, that volume to volume ratio changes. And really, essentially, that cell leads to, even though it's passing through that node, you see a rise in current because there's a change. The volume to volume ratio is different now. Another way to look at it in terms of what I showed earlier, where you have electric field lines, the cell, when it's in this narrow portion, it is occluding quite a bit of the electric field lines in that narrow part of the device. But when it's in that larger channel part, the node, it's occluding less electric field lines. So you see a rise in current. And so what does that all mean? Well, you could have essentially a fancier device that's filled with different nodes and pores, and they're all different sizes. And the current pulse that you see is shown on the right, where it's essentially you can predict what you would see for that current pulse. So what we like to tell people is that with Node-Pore Sensing, we always know where the particle is, whether it's in the small part of the channel or whether it's in the node. And also this really, in the end, helps us to overcome SNR, signal to noise ratio. And I'll explain that in this next slide. So, or just demonstrate it, for instance. So here we have a 4-node device, and you can see how large it is. And what we did was we ran different size colloids through it. And really the nice part, and why we say that you really, the signal to noise ratio is really improved, or what we really say is it doesn't matter as much. And what I mean by that is that since we know we put in a 4-node device, we know that the signal should reflect that 4-node device. And so we expect to see 4 sub-peaks in our data. And that's what you see with this almost 5 micron colloid. Here it is with something that's almost 1 micron, and you can see those red circles corresponds to those peaks where the cell is passing through the nodes. 500 nanometer colloid, it's starting to get a little noisy, but again, we know what we're looking for based upon what our device looks like. And finally, the 50 nanometer colloid, very subjective, but we really could see these very small peaks that correspond to that 50 nanometer colloid going through this very large device, which if you have done Coulter counter measurements, if you've done things with apertures and flow cytometry, you know how difficult that is with your signal to noise ratio, because that particle is just too small when it passes through an aperture. But with Node-Pore Sensing, it really doesn't matter because we know exactly what the signal should look like. Here's another example where what we did was we took that same device on that micron scale, and we took plasma that had been isolated, and it included HIV that had been inactivated. And you can see that what we first saw was in this line of data of current versus time, we see something large pass through, and it was greater than a micron. And we know that size, again, because it's that initial drop off, the current magnitude change gives us the size. And we see there's a 4 subnodes or 4 subpeaks that corresponds to something very real that passed through that through that device. And then, and it turns out that was a fibrin particle. And then HIV, which is on the order of 250 nanometers or so, you know, we looked at our data and we saw something that looked like it was like something weird happened, some very bad noise. But if you do a low pass filtering of that signal, what you see is we actually did measure that an HIV particle. Why? Because we saw those 4 subpeaks that would correspond to that virus particle going through those 4 different nodes. And these are just examples of where we either spiked the plasma with HIV or not. And really, you know, we could tell the difference. And what's really also very nice is that we can actually determine really the concentration of the HIV that passed through, that was in solution, because we know the amount of fluid that passed through the device. So this was just with a 4-node device, very simple. But the question that we were asking is what happens if we get to do something fancier, right? We hadn't really explored the power of Node-Pore Sensing. So this was an example of when we initially tried something where we had varied the spacing between the nodes and changed the dimensions of the nodes themselves. And when a particle passed through, a cell passed through, this is what we got. You can see that there's different types of signal pass, but it's still reflective of the device. but by doing it just a simple FFT, we can tell exactly where the low frequency signals corresponded to a particle passing through those very widely spaced nodes versus higher frequency signals, which correspond to the particle passing through that initial portion where the nodes are very closely spaced together. So here comes my fun part of the story where we really we needed help with signal processing. That was just an example of what we could do, but how could we really harness the power of signal processing? How could we harness this power of node-pore sensing? So, when I first moved to Berkeley, we started doing this, and I knew we needed to have a signal processing expert aboard. And I didn't really know anyone at EECS, but I looked up the course catalog and I found that Mickey Lustig was teaching signal processing. And by the way, Mickey is one of the world's experts on MRI. And he was teaching a course on signal processing. So I just emailed him, asked him if I could go to his class, advertise the project, and see if I could get any takers, any students who would be interested. And Mickey's a great guy. He said, sure, come on over. He didn't know who I was. I gave a 5-minute presentation in his class, and then I ended with who wanted to join me on this journey. And Mickey raised his hand. He said he would love to. And so this has been just an amazing collaboration. It can only happen at Berkeley. And we've been going on this for about 10 years or so. So lucky me, lucky my students, and I think lucky the field, because Mickey really just introduced a whole new level of signal processing with Coulter counter measurements. So what did we learn from Mickey? We learned from Mickey that there are things called Barker codes, and they're finite sequences of plus ones and minus ones. And what's really special about the Barker codes, and I show you a few of the examples, is really the fact that when you autocorrelate a Barker code with itself, you get you have an optimum peak in the center, and then your side lobes are very small. So it's a really great, accurate autocorrelation of itself. So what could we do? So this is just an example of Barker codes if they were pulses. And so here's Barker code 2, which would be a +1 -1 or +1 +1. And you can see that those would be the types of signals that you would see if it were pulses. And there's another example of Barker 5. So the really question really is, so how could you encode this Barker 2 or Barker 5 in an NPS channel, particularly when the NPS pulses all go in one direction? And you can see with the Barkers, they go +1 or -1. So talking with Mickey more, what we realized we could actually combine coding. So in addition, we could use Manchester coding. And what does Manchester coding do? It enables us to translate Barker codes into the ones and zeros instead of the plus ones and minus ones. And I think what is also really cool about what Mickey introduced to us is that all this coding, for instance, Barker coding has been used for sonar detection, and Manchester coding is what is used for T-based Ethernet that we now use in everywhere with a computer. So here's an example of a Barker 3. This is what our microfluidic device would look like. And note that the Barker is supposed to be +1, +1, -1. And this is the signal that we have. And I apologize, we plotted this as the negative of the current. And you can think of everything else that I have. It's just the negative signal of what I've showed you previously. But you can see, again, we're looking for things that are plus and minus. But everything is a plus or really is a 0. So you have 1, 0, 1, etc. And so where we use Manchester encoding is really we're looking at transitions from 1 to 0 would correspond to a +1, or a transition from 0 to 1 would correspond to a -1. So if you look at the signal that's produced and you have those ones and zeros, what you can realize is that first pulse that goes back down to 0, it's going from 1 to 0, so that would correspond to a +1. And at the very end of the pulse, you can see it goes from 0 to 1, that would correspond to -1. And in that way, we can actually, using this Manchester encoding, we can faithfully reproduce a Barker code. So really, what can we use the Barker coding? And that's, I think, what's the most fun part and really adds flexibility to our platform. So, as many of you may know, when you do a Coulter counter measurement with a flow cytometer or a Beckman Coulter counter, you'll get some signal, right? But one of the biggest problems that you have is when you have coincident events. And that way, what you have to do with a coincident event is you have to use things to tease apart the complex signal, or you just throw out the data, which is never really great to do. But here, I'll show you what Barker coding can do. So here's a device. It's not a Barker code, but it's just showing you here's what you would have for a single cell passing through a 2-node device. And then if you have coincidence events, you could see that it's a very complex pulse. And in the old days, my group would just throw out that data, but obviously we're biasing our data. So here's an example. This was done by Mickey, his graduate student, and I had a wonderful master's student from EPFL, Francois Rivest. What we did was we started to work with Barker codes. So this is an example of a Barker code coded sample. This is Barker 7. This is the anticipated signature of a cell passing through and what the autocorrelation would look like with that signal. This is just a simulation to just show, like, okay, what if we have two cells passing through that device? We have a coincidence event. Well, all we need to do is autocorrelate the anticipated signal for a Barker 7 and correspond to our noisy data, and we can pick out the different cells. In this case, there were 3 cells passing through. That was a simulation. But here what we have is really actual measurements where we made a Barker 7 device. And this is the kind of data that we have. And, and first off, we like, oh, it's very easy to see cells, different cells passing through, but we have something very complex at the beginning of that signal. So again, all we need to do is correlate it really with a Barker 7 anticipated signal. And in that way, we can tease apart the coincident events. And we can see that there were 2 cells that passed through initially, but they were, again, a coincident event. So in addition for Barker coding really helping us resolve coincidence events, what we can also determine is really the velocity of cells passing through our channel. And it's surprisingly, at least for us for a while, that these cells, and when they pass through our device, even they're going through at constant pressure, they really are still going at various speeds through the device. That doesn't matter for us for Barker coding because essentially we can correlate our signal with respect to what's the anticipated signal if cells are going through at different speeds. So here what I show you is what Barker code would look like for a cell passing through at various speeds, from fast to slow. Here is some data that we took, and essentially through correlation, essentially we have a library of anticipated signals. We can then determine the speeds of different cells. And this is just an example where, again, we have this library. We correlate that library of anticipated signals with our actual data. And through correlations, we can find out those cells and really when they pass and so forth, which was really great. So really, Node-Pore Sensing is really gives us spatial and temporal information, and we can encode that into our microfluid channel. It allows us to do real-time detection, and it also allows us to resolve coincident events. I think what's really cool is the fact that I have a graduate student who just graduated, Kristen Kotner. She worked with another one of Mickey's graduate students, Alan Dong, both of whom have graduated. And what they were really interested in is how do you multiplex? So, even though I share with this great data, this great sort of strategy of how to handle coincident events, how to do signal processing, our devices, our throughput does not come even close to flow cytometry. We're still in the couple hundred cells per minute. And so really the way to increase throughput, talking with Kristen and Alan, and really is to their motivation and just their innovative ideas. What they realized is they could basically have, like, for instance, 4 channels. Each one has a different code, but you could just have one single set of electrodes. So you wouldn't have to, already you simplified by multiplexing, and you're increasing throughput. So what do I mean by here? So here's 4 devices. They each have different codes. They would each have a different anticipated signal to be measured. And then cells would pass through, and some cells would go through one that's labeled code A, some cells will go through code B, and so forth. But you're doing one single measurement. So, how would you be able to detect your signal that the cell went through whichever device? So this is where, again, we know what the code should be, what signal it should produce. You would start to build your library of the anticipated signals, and you would start to correlate your signal with that library. And so something complex that's shown here in the figure labeled C, we can see that first signal or actually corresponded to a cell passing through code A. The middle signal, which is shaded in green, corresponds to a cell passing through the fourth device, code D, and then the red corresponds to a cell passing through code C. So by knowing what the signal should be and correlating that signal with your data, then you're able to really pick out where cells have gone in which device and so forth. So that was all great. So we still ended up, even though I'm saying that signal to noise ratio has slightly a different meaning for our Node-Pore sensing. As long as we know the anticipated signal, we can extract it out. We can do an FFT, we can do a correlation. But at the same time, we do reach a limit, as you could see before when we were trying to measure these 50 nanometer colloids in a 4-node device that was huge. And so, and also remember what I said was that our signal, the anticipated signal, really is proportional to the volume to volume ratio of the cell with respect to the device or the pore. At some point, you do reach that limit where your signal to noise ratio can't be overcome. So again, through Alan and Mickey, what we've now come up with something that we call metal pad sensing, and that completely obviates the needs for nodes. Nodes do increase the volume of the device, but with metal pad sensing, we don't need those nodes. And so our signal to noise ratio already is great. So here's just an example where Alan had created essentially metal pad sensing consists of contact pads that are contactless pads in the middle of the channel, as you see here. What he did was he ended up putting his metal pad sensor on top of a Node-Pore Sensing microfluidic device. You can see we have various labels for this particular device. It has what we call contraction sensing, a segment, and that just corresponds that we're measuring the mechanical properties of cells they have to squeeze through. But regardless, what Alan did was this is what the measurement that we see if a cell passes through. So this is right now what I'm showing you is simulated data. But here's a cell passing through, and we see the cell passing through a part of the device where it's a sizing channel, through a contraction part of the device, and a recovery device. Essentially, these 3 pulses are being separated by the nodes, those 2 nodes there. But then this is at very low frequency. But at high frequency, what you see something very different. Instead of 3 pulses, you see sharp pulses that are all sort of evenly spaced underneath what would be the sizing pulse, the contraction pulse, and the recovery pulse. So where does this come from? What does it really mean? So this is really the genius of Mickey and Alan. What they realized is that you can model the pads, the voltage pads, the contactless pads as essentially a circuit of resistors. And essentially, because you have also the dielectric or the double bilayer surrounding these contactless pads, that can be modeled as a capacitor. So at different frequencies, you can see what will happen as the cell passes through, or what happens with those electric field lines. So at the higher frequencies, essentially almost all the current as it goes from that voltage pad it actually travels through this sort of metal U. It's bypassing the current is really bypassing the fluid between those two electrodes that are attached to that metal U. And so the electric field is very low when that happens at high frequencies. So in some sense, that in between those two electrodes that are connected by the metal U, that actually becomes our node. And so as the cell passes through, it's not occluding as many electric field lines as it were before those pads. And so as a result, as you increase the frequency and where the current is being diverted into these metal U's, the contactless pads, what you see is essentially the development of the current being flowing through those metal pads. And essentially the cells are really going through the nodes, and you can see that the field lines and the current that we measure drastically changes from something that's sort of obtuse and diffuse into these very sharp peaks. So what can we use metal pad sensing for? I really should start with that. It greatly improves our signal to noise ratio because the volume of the channel is not as large anymore because the nodes are created by high frequency. It also gives us a really good sense of where the cell is, an accurate cell position, and actually the velocity. And this becomes important when we want to do mechanophenotyping, which in itself is a different talk, but it really gives us a sense of really a more complete physical portrait of the cell. So I'll just end by saying that with Node-Pore Sensing, again, I really want to stress that you can put spatial and temporal information. You can do real-time detection. You can do resolving coincidence events, and you can do multiplexing. So instead of a few hundred cells per minute, you're already up to 1,000 or more cells per minute. So not close to facts, but given the information that we have, we get quite a bit of information about cells, particles of different sizes passing through. We're not limited to a certain size of the aperture in a culture counter. And I'd like to thank the people who have worked on this project. You can see there's quite a number of students throughout the years, and this is just a picture of my current group. And I'd like to acknowledge all my funding sources. And with that, I just would say thank you very much for your time. And if you have any questions, I'm happy to answer. Thank you.